In lesson 10.1, we're going to look at exponential functions. This is kind of a lead-in to what this whole chapter is about, which is logarithms. First of all, defining what an exponential function is. In an exponential function like y equals 2 to the x, basically an exponential function means your variable x is going to be up in an exponent or a power. The base is the constant, and the exponent is a variable or has a variable in it. Okay, so we're going to look at the graph, or they look at the graph here of y equals 2 to the power of x. They make a table, and this is something you could put in y equals on your calculator too, but notice if they put in -3, you'd have 2 to the -3rd power right here. That you move it down, make it 1 over 2 to the third, which is 1/8. Okay, so anytime you have a negative exponent, you're going to get a fraction. Put in -2, that's 2 to the -2nd power. Move it down, make it a fraction, move it down, make it 1 over 2 squared, which is 1/4. -1, 2 to the -1st, 1 over 2 to the first power, which is a half. 0 power is 1. Okay, and then they do put in a half, so it's 2 to the 1/2 power, which is square root 2. So they pick one in between integers there, just to show you what's going on with that. And then 1 is 2 to the first, or 2, 4, 8. Now they don't go any further, but as they get to 4, 2 to the 4th power, this is going to start shooting up real fast. So you can kind of see here what the graph is doing. They plot these points, and basically there's a horizontal asymptote on the x-axis. As we go out this way to negative infinity, it's going to keep getting closer and closer and closer to the x-axis, but never actually get there. Key point here is it goes through 0, 1, okay? And they also say that the domain includes irrational numbers, so it's not just integers. We can put in things in between, and then it's going to start shooting up really fast here and keep going out as the powers get bigger. So the domain is all real numbers. Notice it never gets below the x-axis, so for this example, the range, or the y values, the output values, are all positive numbers. Some key points, and kind of the general form here for any exponential function is y equals a times b to a power of x, and I'll put a dot in between. A cannot be 0. The base right here, b, this value right here, has to be greater than 0. And it won't be 1, because 1 to any power would be 1. So some facts about it. It's continuous and 1 to 1, so it's basically got continuity. The domain is the set of all real numbers, so x basically is all real numbers, everything on the number line from negative infinity to positive infinity. The x-axis is a horizontal asymptote. The range is a set of all positive numbers if a is bigger than 0. So then it will be above the x-axis, or it'll be positives. If a is less than 0, so if this right here, this value was small, it was a negative, basically it's going to be flipped on the other side of the x-axis, and you wouldn't have anything up in the positives. The graph contains the point 0a, so whatever a is, the y-intercept is going to be 0 comma that value. You know, like if you had y equals 2 times 4 to the x, then 0, 2 would be a y-intercept, 0 comma a. If I had y equals 3 times 1/2 to the x, then 0 comma 3 is where it would intercept the y-axis. So this is always telling me the y-intercept. The base of an exponential decay. Then we get into exponential growth and exponential decay. Actually, these are reflections across the y-axis. As you can see, they've got both of these pictured here. But then we get into exponential growth and exponential decay. Basically, it's a curve. Exponential growth is growing from left to right. So the curve is increasing from left to right. So this curve right here would have exponential growth from left to right. This one is actually going down as we go from left to right, so that would be exponential decay. The base of an exponential decay function, so what you're raising to that power, is always a fraction between 0 and 1, or decimal. And that's kind of what you're looking for. And that's what this key concept points out here. If a is bigger than 0 and the base is bigger than 1, it's going to be exponential growth. We'll look at some examples here in a second. If a is bigger than 0, so it's a positive out in front. So a is a positive in the general form for an exponential function. Or I'm sorry, if the base is, a is positive, but the base is between 0 and 1, so this tells me a fraction or decimal between 0 and 1, it's going to be exponential decay. So let's look at some examples of that. Here's some examples. If I have y equals 1/5, notice right here, my base is 1/5, then that means it's going to be exponential decay because that's a fraction between 0 and 1. Notice on this one, I have a 4 there. It's bigger than 1. So that's going to be exponential growth because the base 4 is bigger than 1. This one also, if I look right there, it's a 1.2 exponential growth. 1.2 is bigger than 1. Exponential functions are frequently used to model the growth or decay of population. You can use the y-intercept and one other point on the graph to write the equation of an exponential function. So if we know what the y-intercept is or what a is, because a is always going to be the y-intercept, and we know another point, we can write the equation. And we'll look at an example here. Now this is a word problem example, and I'll do another one at the end. But in 1983 there were 102,000 farms in Minnesota, but by 1998 this number had dropped to 80,000. Write an exponential function in this form that could be used to model the farm population y of Minnesota. Write it in terms of x, which is the number of years since 1983. So that's what x stands for. So for 1983, the time x, so that's the kind of the starting year, so they're saying x equals 0. The initial population in 1983 is 102,000. Thus the y-intercept, or the value of a, okay, is where you're starting at, is 102,000. For the time, then we got to figure out how many years is it from 83 to 98, which is kind of our ending time. So they do some subtraction here, and that's 15 years after the initial year of 1983. It's at 80,000 then. It had dropped to 80,000. So you substitute these values and the value of a into the general form of an exponential function, approximate the value of b. So let's take a look at what they did here. In for y, they put the ending amount. In for a, so that value right there, that's the starting amount, or in 1983 what the population was, which is 120,000. Okay, and we're going to solve for b, and then x is the number of years, okay, because they said in terms of x the number of years, so that's why the b is to the 15th power here. So we're going to solve this for b. So what they did is they actually took 80,000 and they divided by 102,000 here to get rid of it. So they took 80,000 and divided by 102,000. And they rounded it off. That's where that 0.78 came from. Now if that's b to the 15th power, you take the 15th root of 0.78 on your calculator. Okay? And if you do that, if you have a graphing calculator, use the one with x, you got to put the 15 in first, and then you do the 15th root. It's under the math menu. Put the 15 in, hit the math menu, 0.87, or I'm sorry, 0.78, that should be. And you get, if you hit equals, you get this decimal right here. And they round that off to about 0.98, so they went to the nearest hundredth. So now you go back and write the function. Okay, we're going to leave y and x in there, kind of like you've done for other functions. Y equals the starting and population of 102,000 times 0.98 would be the base that we got to the x power. Notice how they put y and x back in. We put values in up here for y and x to help us solve for b, to find that b. It's kind of like what you've done with linear equations, trying to find the y-intercept and things like that when you put in values or a point. Okay? So then they say, suppose the number of farms in Minnesota continues to decline at that same rate. estimate the number of farms in 2010. Well, we have to figure out for 2010 what x is, and x, remember, is the number of years after 1983. So if you take 2010 and you subtract off 1983, you get 27. So x is 27. So that means notice how they put 27 right in here, and you'd have to do the power first, 0.98 to the 27th, and then multiply it by 102,000, and notice they rounded it off to the nearest whole number, so 59,115. Alright, exponential equations and inequalities. All the properties of rational exponents apply to irrational exponents. So all our property rules that we've looked at apply. So if you look here at this first example, I have 2 to the square root 5 power times 2 to the square root 3 power. It goes back to this rule, 5x squared times x to the third. I add the exponents, okay, which in this case you could write that as x to the fifth. Or if I had 2 squared times 2 to the third, that's 2 to the fifth power. And you could actually figure that out if the base was 2, but you add the exponents. That's what we're doing here. Now notice, you can't simplify that because I can't actually add square root 5 and square root 3. They're not like radical terms. So that's how it would simplify. Power to a power rule, if I have x squared to an outside power of 3, it's x to the sixth. Okay, I multiply the 2 and 3. Well, that's what they're doing here. Power to an outside power. Now these you multiply, so I multiply the things underneath, so it'd be 7 to the square root 6 power. Okay, so those power to a power and the product rule apply even if they're irrational exponents with roots in them. The next example here, the following property is useful for solving exponential equations. Exponential equations are which variables occur in the exponents. So notice what they say here, if you have 2 to the x power and you said that has to equal 2 to the eighth, if this base is the same, which it is, you basically can set that equal to that and solve. Now this one you just have x equals 8. But if you had something like this, if I had 2 to the 2x power equals 2 to the 8th, basically if these bases are the same, I can set 2x equal to 8, solve for x, and x would be 4. Okay, so that just gives you another example. You set the powers equal to each other if the bases are the same. Sometimes you need to get the bases the same. Okay, so in this section we're going to look at that. So here's what we have, 3 to the 2n plus 1 power equals 81. So what I want to do is I want to say, can I write those with the same base? Now, 3 to the power of 2n plus 1, but this right here can be written as 3 to a power, 3 to the fourth power. So they're going to give you numbers that you can write as the same base. So 3 to the fourth power is 81. Now that I have these bases, equal to each other, I can set that exponent equal to that. So 2n plus 1 is equal to 4. I subtract 1, so 2n is 3. I divide by 2. So n is 3 halves, which is what they're saying right there. Next example down here, I have 4 to the 2x power equals 8 to the x minus 1 power. If you look here at these two bases, I can't write 8 as 4 to a power, but I can actually write this one as 2 squared. 4 is 2 squared. Now that power of 2x goes on the outside of the parentheses then. This one can be written as 2 cubed, and then my power that was on the 8 goes on the outside of parentheses. Now my power rule applies. Power to an outside power, I multiply exponents. So 2x times 2 is 4x. Here, I multiply exponents. Now I'm really taking 3 times x minus 1, where I have to distribute, which is going to be 3x minus 3. So it's 2 to the 3x minus 3 power. Now I have them in the same base, so I can set my powers equal to each other, and I'm going to subtract 3x. So x is equal to negative 3. So in that case, I had to change both original bases to a smaller base, and that's sometimes what you need to do. The following property is useful for solving inequalities involving exponential functions or exponential inequalities. So kind of the same thing we just did with equations. If I have 5 to a power of x is less than 5 to the fourth, Okay, you're doing the same thing. When that was an equal sign, you set x is equal to 4. Well, now I say x is less than 4. That's what they're saying right there. So now these are going to be inequalities very similar. 4 to the 3p minus 1 is greater than 1 over 256. Now, just a little hint, when that starts out as a fraction, and we're going to write with the same base. Okay, so that's starting out as a fraction. What you want to check for is that number on the bottom. 256 is 4 to the 4th power. Okay? But because it's 1 over 256, 4 to the negative 4th power is 1 over 256. So I'm going to write this as 4 to the negative 4th. Remember, because 4 to the negative 4th would be 1 over 4 to the 4th. 4 to the 4th is 256, so that equals that. And we have this, 4 to the 3p minus 1 is greater than that. Now that I have the bases the same, it's not an equal sign now, we're just going to say this exponent is greater than this exponent, and then we're going to solve it. We're going to add 1, so 3p is greater than negative 3. We're going to divide by 3, so p is bigger than negative 1. And they go through and they show it checks out here if you want to go ahead and plug it back in. Okay, last example. Write an exponential equation given 2 coordinates. This is kind of like the word problem example earlier that referred to population in Minnesota, except for now this is going to be more like what you're going to get. So notice they give me, that goes through this, so that's my y-intercept. And remember, the y-intercept, this value is always a, and then this is your xy value. Okay, so what you want to do is you want to write down the general form for an exponential function. And now I want to plug in my values. So a is negative 2 right there. For x, I'm going to plug in negative 2, and for y, I'm going to plug in negative 32. So here's what you want to do. In for y, we're putting negative 32. In for a, we're putting negative 2. We're going to solve for b, so that remains the variable in my equation. And then I have to the negative 2nd power. Now we'll talk about, some of these you aren't going to have a negative power on that. We'll talk about how to deal with that in a second here. So what I want to do is I want to get this alone first. So I got to divide by this negative 2 that's out in front. So I have 16 is equal to b to the negative 2nd power. Now that doesn't say b squared, it says b to the negative 2nd. Okay? What you want to do is, if you think about b to the negative 2nd is 1 over b squared. So you're really dealing with reciprocals when you're talking about negative powers. So what you want to do is, I'm just going to change this to b squared, and then you want to take the reciprocal of this side. And this is only if that's a negative power. If that was just b squared, you'd take the square root of both sides. So, but it's b to the negative 2nd, then this becomes 1 over 16, because that's the reciprocal. Now I take the square root of 1/16, okay? And you only need the positive. There technically is 2 square roots, but you only need the positive here because the base has to be a positive number. So the square root of 1/16 is 1/4. So b is 1/4. Now we take that and we write the equation then. At the end, the equation in exponential form has to have y and x in it, so it's y equals a, which is negative 2, times the base of 1/4 to a power of x. Now, to relate it to something we talked about earlier, notice the base is a fraction, so this would be an exponential decay. It's between 0 and 1, 1/4. That thing you're raising to the x power is between 0 and 1 fraction, so it would be exponential decay. Now, a is negative here, which means when you graph this, it's going to be below the x-axis. Okay? All your values are going to be negative for y. And that's Lesson 10.1.